When I started working on embedded systems over 10 years ago, the developer experience was often determined by your microcontroller vendor, which meant writing in C, using the vendor's compiler and IDE, their in-circuit debugger hardware, and working in Windows. Minimizing memory safety issues meant finding a static analysis tool, an easy thing to punt on unless your project requires it. But over the past few years, things have really changed. Rust, the memory-safe alternative to C, has started making inroads into the embedded space. And technologies like Language Server Protocol and LLVM have made it easier than ever to move away from vendor tooling for bare metal projects. So I'd like to show you how to get set up for embedded software development with Rust. We're going to start from scratch, and we're not going to skimp on the details because I want you to see not just the destination, but how we got there, so that you can use this process to get started with whatever hardware you want to work with. And by the end of the video, we'll have a solid foundation we can build on for future projects. So fire up your terminal, and let's get started. If you're new to Rust, the first thing you'll need to do is install RustUp, which is Rust's toolchain manager. To download it, you'll need to visit rustlang.org/tools/install. If you're using a Mac or Linux, you can just copy this curl command over to your terminal. And if you're using Windows, they've got an installer executable you can download here. If you've already got RustUp installed, it wouldn't hurt to run the update command, as the language releases a new version every 6 weeks. RustUp gives us everything we need to start developing, including a compiler called rustc and Cargo, which is a package manager and build tool, and that's what we'll be using most of the time. RustUp and Cargo also manage the installation of other tools we'll need, but more on that later. For now, let's move on to selecting an editor or IDE to use for development. The good news is that you've got plenty of options. Gone are the days when you had to rely on a vendor-built IDE that only ran on Windows to build your embedded projects. All you really need is a decent editor for Rust, ideally one with LSP support. If you're a fan of JetBrains IDEs, there's RustRover. If you love the speed and configurability of NeoVim, you can use that. But I'm mostly going to be using VS Code for the projects on this channel. It's not the fastest editor out there, but it is pretty easy to get up and running. So how do we get VS Code set up for Rust? There's really only one must-have plugin, and that's Rust Analyzer. As an LSP implementation, it's going to give you tons of handy features like code completion, go-to definition, and type inference, so you're going to want to make sure that gets installed. Some other nice-to-have but not required plugins are Even Better TOML for improved TOML syntax highlighting, AirLens for better air highlighting, and Crates to help you see dependency version information. All right, we've got Rust, we've got our editor. Let's move on to hardware. At the top of the episode, I said you could follow along with whatever hardware you want to use, and that's mostly true. The rustc compiler is a front end for LLVM, which means it's very easy to cross-compile for various core architectures and environments. At the time of making this video in early 2024, the Rust compiler has excellent support for microcontrollers that have ARM Cortex-M or RISC-V processors. In my case, I'm using the BBC Microbit version 2, which has an ARM Cortex-M4 based microcontroller, an LED matrix, some buttons, a microphone and speaker, and an accelerometer to play around with. And it's cheap, less than $20 at SparkFun. So how do I get this thing hooked up to my computer? Do I need some expensive in-circuit debugger hardware from my microcontroller vendor? Nope, just a micro USB cable. The nice thing about working with project or evaluation boards is that they usually include a secondary microcontroller that acts as a USB debugging and programming interface to the host machine. Now, how do we build code for this thing? This brings us to the topic of cross-compilation. If I built a project in Rust right now, it would run fine on my host machine, but that's obviously not what we need for our project board. The way to specify a different target in rustc is through a target triple. This is composed of a core and sub-architecture, an optional vendor and/or operating system, and an environment or ABI. So what target do I need for this board? Well, the first element is architecture, so it's time to pull up the product specification and find out the specific microcontroller that it's using. Do a quick search for the microbit datasheet, and it's got a Nordic NRF52833 microcontroller which has an ARM Cortex M4 processor with an FPU. Now, if we go to ARM's website, we can see that the M4s have an ARM v7 EM architecture, and the instruction set is thumb or thumb 2. So the next thing I'm going to do is head on over to Rust's platform support page and search for ARM v7 EM core architecture, and there we go. There are 2 variants for bare metal, one with the hard float. That's the one we're going to need. Now, as you can see here, there are a ton of potential systems you can target, and the only one that gets installed by default is the one for your host machine. So we'll need to manually add support for our board, and we'll do this through the rustup target add command. And then you can see which targets we've installed by entering rustup show. All right, I think we're ready. Let's start our first bare metal Rust project. Starting a new project in Rust is easy. We just enter cargo new, followed by the name of the project, and that'll create a new directory containing our project. So let's go in there and see what that gave us. We've got a new Git repository. We've got a cargo.toml file that contains some metadata about our project, and any dependencies that we add will get called out here. And we've got a source directory that contains a main.rs file. And that's got a little boilerplate hello world code. Nice. So let's go into VS Code and start playing around. Now, the first thing you'll notice is that there are a few new files in our project. So what's going on there? The Rust Analyzer plugin will occasionally run a cargo command called check in the background, and that checks our code and our dependencies for errors. And it does this by actually compiling the code, and that's what produces these other artifacts. We've got cargo.lock, which is the very specific dependencies we're using in our project, and the target file, which is where our compiled artifacts live. To get started, we need to make some changes to our main.rs file. By default, Rust assumes that our application is running in an operating system, and so our main function accepts arguments that we don't want or need. There's also a standard library that's getting included in the prelude ahead of our main function, which is giving us the ability to use this printline macro to standard out, and again, we can't use that. So let's tell the compiler that we don't want it to include the standard library or its main function, and we'll do this through the nostud and nomain attributes at the top of the file. Now, LSP newbies will appreciate this. Our Rust Analyzer plugin is giving us some autocomplete options from the built-in attributes. No stud, no main. Okay, we've gone about as far as we can on our own without trying to reinvent the wheel. We need to pull in some third-party code, so it's time that we talk about dependency management. Yes, dependency management, built into a systems language. If you're coming from C or C++, this is going to feel unfamiliar, fantastic, life-changing. I don't know, but it's pretty great. The Rust project maintains a registry at crates.io, and this is where you'll find all sorts of libraries that you can import into your projects, and pretty much all of them are open source on GitHub. So let's see what this looks like in practice by adding our first dependency, which answers the question, how does our code get properly located in our microcontroller's memory map? This is addressed in the Cortex-M RT crate, which includes a linker script that'll work with any ARM Cortex-M based devices. Let's bring up the docs for this crate. Another crazy awesome feature of Rust where a certain type of comment that you leave in your source files can generate documentation that looks like this. So let's see. This will locate our vector table to map interrupt and exception handlers. It'll initialize our static variables and enable the FPU before our main function is called. And it gives us some function attributes to identify our main function and our interrupt and exception handlers. Great. So what does it need from us? It's going to be looking for this memory.x file, which minimally needs to contain both the start address and size of the flash and RAM regions of memory for our specific microcontroller. That sounds reasonable. So let's revisit our board's product specification and find out a bit more about the microcontroller it's using. It's got the Nordic NRF52 833, and it's got 528 kilobytes of flash and 128 kilobytes of RAM. Now that's our size taken care of, so now we just need those start addresses, and for that we will need the microcontroller's datasheet, which Microbit has kindly linked here. And here, after a fashion. Okay, so let's do a search for memory map. There we go. All right, the flash starts at 0, and the RAM starts half a gigabyte later. Let's add this as our first dependency using cargo add. And then we can recheck the cargo.toml file, and we can see it's there with the latest version information. Now let's also add the memory.x file that it wants. And we'll do a little copy paste. Flash starts at 0 and is 512 kilobytes. RAM starts half a gigabyte later, it's 128 kilobytes. Now we can also update our main function with the entry attribute that our Cortex MRT crate is looking for. And one last note about Rust Analyzer's autocomplete suggestion. If it finds what you're looking for within a dependency and you click on it, it'll automatically import that item into scope for you. The entry attribute requires that the function signature never return, and then we'll actually make it never return. We also need to let the Rust compiler know that it needs to run the linker script anytime it rebuilds our project, and we do this by passing in some arguments. Now, passing in both the target and linker arguments anytime we want to rebuild the project is going to get tedious very fast, so it's time to do a little housekeeping. We can create a cargo configuration file for our project that includes those target and linker arguments. Now, anytime we run cargo build, it'll automatically apply that target and those Rust compiler flags. Sometimes you'll find Rust Analyzer needs a little manual intervention to refresh state. And this leads us to another issue. Remember how I said that our Rust Analyzer plugin will occasionally compile our project in the background to check for errors? Unfortunately, it's running that compilation under our host architecture, which is not ideal. We need to tell it to only check our target of interest, otherwise we're going to get some strange errors. Let's add another configuration file, this one for VS Code and our Rust Analyzer plugin. Now it's only going to check our bare metal target, and we'll restart Rust Analyzer. Hey, error's gone. Now, Rust Analyzer seems happy, but I'm going to run cargo check just to make sure. Yeah, panic handler function required but not found. Is it time to panic? The error is telling us that we're missing a panic handler. So what's a panic, you might ask? In Rust, for normal, recoverable errors, you would just return a result type in the error state from whatever function you're in. And so a panic is basically reserved for fatal errors. It's when you've hit some intractable issue, like failing an assertion, and the panic handler is where your code goes to die. I think there's enough to say about panicking, particularly its implications in an embedded environment, to justify a standalone video, so for right now we'll just cover the basics. Your panic handler is just another function that's marked with the panic handler attribute that has a very specific function signature. It takes a reference to a panic info argument, and it never returns. This will get called when your code or one of your dependencies calls the panic macro directly, or when trying to unwrap a result or option in an invalid state. And in some cases, the compiler will add a branch to panic. For example, if you're accessing array elements by index, the compiler will insert a runtime bounds check into your code that panics on an out-of-bounds access. So we need this thing. Even if it doesn't get linked in, the compiler still wants it defined. The easiest option is just to pull in the panic halt crate, which does the absolute bare minimum. It's got the right function signature and an infinite loop inside. Definitely not what we'd want when deploying a product, but for debugging on the bench, this is fine. So let's add it to our project. And to make sure the compiler sees it, we'll add it to our main.rs file. Okay, moment of truth. Rust Analyzer and Cargo Check both seem happy, so the code should build. Here we go. Hey, it builds. The ELF file containing our program is located in the target directory in either the debug or release folder depending on how we built it. Debug's the default. Now, let's take a look at this file real quick before we try moving it over to our microcontroller, and this leads us to a few other tools to install, the first one through rustup. We're going to add the LLVM tools component, which gives us bin utils like size, readobj, and objdump for getting info about the binary and viewing disassembly. The ergonomics of calling these directly for our target binary aren't great, so we're also going to install a subcommand for cargo called cargo bin utils, which is just a wrapper around LLVM tools that makes them easier to use. So yes, cargo is extensible. You can create your own applications that can be invoked as cargo subcommands. For cargo bin utils, all we need to do is specify the LLVM tool we want. Let's try size. Nice, we can see the linker script's handiwork. It's correctly locating our code somewhere in the text flash section of memory just after our vector table. And we don't have any global static data, but if we did, we can see the BSS and data sections are located in the RAM region we defined in our memory.x file. Okay, that all looks good. Let's actually try and flash this to our board. To do that, we'll install one last cargo subcommand, cargo embed. This is going to both rebuild our code and talk with our secondary debug microcontroller, send it our binary, and have it program our primary microcontroller. It's also going to allow us to connect a debugger so that we can set breakpoints, modify memory, and step through code. To get cargo embed set up, we minimally need to specify the microcontroller we'll be programming. Let's see what it supports. Okay, well, let's just look for something that looks like the microbits NRF52833. Yeah, there it is. So let's try that. Huh. Oh. Yeah. Let's try that again. Sweet. It says erased and programmed. I'm going to dump this chip info into a configuration file so that I don't have to re-enter it the next time we run it. The cargo embed subcommand is going to be looking for an embed.toml file, and we'll add our chip info there. Let's retry. Still works. This is great. We've got our controller erased, programmed, and running. Presumably. That program does literally nothing, so it's a little hard to tell. This brings us to the last topic on our embedded Rust tooling adventure, debugging. I'll be honest, when debugging embedded applications, I personally prefer using log or print line style messages over a full-blown debugger. If your code is trying to maintain communication with one or more connected devices, then hitting a breakpoint that halts the CPU can be massively disruptive to the timing of those interfaces, and ironically can make debugging more difficult by introducing new issues. This brings us to our first debugging option, real-time transfer or RTT. For those unfamiliar, it's basically a way to exchange data between your host computer and your target microcontroller using its debug interface. So for example, if you want to fire out print line messages to the host, you're basically just writing to an in-memory ring buffer that gets read by the debugger, which means it's very fast. The RTT target crate has what we need. It's pretty simple. We have to call an initialization macro and then a print line macro with any data we want to send to the host. It does require an implementation for critical section, which we don't currently have, but the Cortex-M crate has us covered. I'll need to add the optional critical section single core feature for my single core controller. So let's add both of these to the project. Cargo embed is going to facilitate the RTT, so we need to enable it via our embed.toml file. In our code, we'll just add that initialization macro and a little hello world code. The Cortex-M crate also has an assembly no-op instruction we can use to create a little bootleg delay. Alright, let's try it out. Cool, pretty simple, as advertised. But sometimes we need a more hardcore option, something providing the standard debugging experience of setting breakpoints, viewing disassembly, and manipulating memory. And I think we might have to go old school. GDB has been the standard tool for debugging C and C++ applications for over 30 years, and it works with Rust as well. Many of you may have used it in the past and possibly already have it installed in your machine. But to debug an ARM Cortex-M-based microcontroller, we're going to need the ARM toolchain version of GDB, and the easiest way to get that will vary based on the OS you're running. On Linux, you can use your package manager to install GDB multi-arch. On Windows, ARM provides an executable that you can download here, and you'll need to add it to your path. And on my Mac, the easiest thing to do is just to use brew. To connect to an embedded target, GDB will need a proxy to send commands to, and Cargo Embed will do this for us. We just need to update our embed.toml configuration to enable the GDB server, and halt on reset to wait for GDB to connect. And we'll switch off RTT for now. Let's modify our main function, get rid of the RTT, and just increment a local variable we can watch. Let's make our terminal a little bigger and split it. Alright, now when we run Cargo Embed, it's going to rebuild our code and block while running our GDB stub. And we can run GDB in another terminal passing in our target binary. Connect to our target. You may get a lot of spurious warnings like me, and you can get rid of them just by dumping the standard error, which I'm going to do here. There we go. And now we can do all sorts of GDB things. We can check out the register values. We're straight out of reset, so everything's been initialized. Stack pointers are at the very top of our RAM region. Let's check out the disassembly for this reset function. Okay, let's demangle those assembly symbols. That's better. So the first thing our reset function does is call the pre-init function. Let's see where that goes. Yeah, we never defined one, so it just returns us to where we came from. And the rest of this reset function is just initializing our BSS and data sections and our FPU before it eventually calls our main function. Let's skip ahead and set a breakpoint somewhere in main. How about where we increment x? Then run until we get there. Then we can check out the local variable values and run the loop and get back to our breakpoint. We can also see the address of a variable. X is on the stack. And modify variable values. We can also check out and remove our breakpoints. And we can reset our microcontroller. You get the idea. And that about does it for this one. We've got a great setup for embedded Rust projects going forward, and we have some idea about how to debug them. If you found anything in this video useful, or even if you didn't, you're still watching, hit that like and subscribe button and help us out. Thanks again for watching, and I'll see you in the next one. Ferris. Thank you.